Hello to everybody. Welcome to be here. Thank you for accepting our invitation to this Nobel lecture. We are so pleased to have such a special guest this afternoon. Have to say that for the week of the celebration that we have during this period, we decided to organize a series of Nobel lectures. So this is the first of a long series that we have in forthcoming months. Tomorrow we will have a dialogue with Roger Penrose and also with Joseph Stiglitz, so Nobel Prize in Economics, and then we will have next week Fields Medal, Alessio Figalli, and many other very important guests. So we are so happy that we have reached this very important moment in the celebrations for the 800 years of the university, from the foundation of the University of Padua. Today we have Professor Gerardus at Hooft, so Nobel Prize in 1999 in physics for his contribution to the quantum structure of the electroweak interaction, so elementary particle physics. It's impossible to synthesize, to squish up such a wonderful career, so now I'm going to give the floor to Professor Fabio Zwirner. Have just to add a point, we are also, for another reason, so happy to have Professor Tuf as our guest today, because I discovered that he's also a wonderful communicator of science, because I read that an asteroid has been dedicated in his name, and he wrote a wonderful constitution for this asteroid. My invitation is to read this constitution because it's wonderful. It's an ideal constitution for the inhabitants of a virtual world outside. And he also wrote a wonderful, different books, of course, several books, but also a wonderful book that I read years ago about the time in powers of 10. So a wonderful voyage in the dimensions of time. So it's a great pleasure to welcome at the University of Padua for this moment. Professor Tuf has been invited also in Padua for another meeting that is going on in these hours here in the Botanical Garden, organized by our philosophers in the university, dedicated to a very ambitious topic, so eternity between space and time. So now I give the floor to my colleague, Professor Zwirner, that is pro-rector for the research of our university, that is also a colleague of our guest. So Fabio, floor for you.
Good afternoon, and welcome to you all, on behalf of Rector Daniela Mappelli. This morning, our university celebrated the opening of its 800th academic year with the participation of the President of the Republic, Sergio Mattarella, and the President of the European Parliament, Roberta Metsola. And there is no better way of concluding such an important day for our university than a public lecture given by one of the greatest living scientists, Professor Gerardus Hooft, who in 1999 shared with Martinus Veltman the Nobel Prize in Physics for the reasons that Telmo just mentioned. That was a fundamental contribution to what is called today the standard theory of strong and electroweak interactions, and an extraordinary success in the confrontation with infinity that gives the title to today's lecture. In his career, besides providing numerous very important contributions to quantum field theory, in particular to the so-called quantum gauge theories that generalize the quantum theory of electromagnetism, the theoretical research of Professor Hooft has also addressed quantum gravity, black holes, and the foundations of quantum mechanics. Before the Nobel Prize, he received many of the most prestigious prizes in physics and in science at large: the Danny Heinemann Prize, the Wolf Prize of the State of Israel, the Spinoza Prize, the High Energy Physics Prize of the European Physical Society, just to mention a few in a very long list. And he has collected honorary degrees from prestigious institutions all over the world. The asteroid was mentioned, and in addition, Professor Hooft is also officer of the French Légion d'honneur. He has also been very active in outreach. One book has already been quoted by Telmo, Time in Powers of 10, written with Stefan van Doren. And another book that I read personally and I found charming and very useful is a book called, in English, In Search of the Ultimate Building Blocks. That is an older book from 1996. I think I shouldn't take more time from the lecture, so I leave the floor again directly to Professor Hooft for his lecture. Welcome.
Thank you very much, Fabio, and it is my great pleasure to be here to help you celebrate the 8th century anniversary of this university. It's a great occasion to be here, and I could not refuse this invitation. What you see here projected on the screen is one aspect of infinity. Actually, it is a very tiny part of a fantastic mathematical structure called a fractal. In this case, the Mandelbrot fractal. The Mandelbrot fractal is a structure that you can look from close up by enlarging it so much that it would take the size of the solar system. And then if it would take the size of the solar system and you zoom it in at a very special spot, you see structures where still at the millimeter and beyond you see more and more and more details. So the infinity lies really in the third dimension, that focusing into details. The details go on forever. So it's a beautiful example of infinity. Now this is an infinity in mathematics, and I'll mainly talk about infinities that we encounter in the physical world. And there are different kinds of infinities, but in a way just about as beautiful as this one. And for instance, the first instant that scientists got into contact with the problem of infinity in this world was Isaac Newton. Newton is famous for understanding for the first time exactly how the laws of gravity work on planets when they go around the sun in circles, but also it acts on the moon while it goes around the sun. And actually gravity also works in our daily lives. When I take this thing, I drop it on the floor, then it's gravity that pulls it down, basically. But Newton, for the first time, understood how gravity works by first defining the notion of velocity. So where a planet is, or where a star, or where an atom is easy to indicate in terms of indices, but of coordinates, I mean. But how do you define velocity of something? It sounds so simple. You look at where the object is at one particular time. Can you see this thing? Yes. And you look at it when it is a little time later, where it has moved. Then you find that it has displaced itself. That displacement, then you divide that number by the time it took. So this delta t is the time it takes to make one step on this top picture, and delta x is the displacement that you get as a result of that. Now you take the ratio of the two, then you get something that looks like velocity, but it's not quite, because this may not have been the exact orbit. The orbit is as if it is divided into integer parts. No, you could take the same orbit and divide it in smaller parts, and then again take that ratio, you again get the velocity. Now Newton discovered, simultaneously with a colleague of him, Gottfried Leibniz, and what they discovered was that you can take a continuous curve and then define velocity as the limit, where you take shorter and shorter times, then you find the displacement will be shorter as well. You divide the two, and that division approaches a constant when delta t is infinitesimally small, and delta x also. So this sounds, for many of us here, this sounds like totally trivial and normal and, well, self-explanatory. But actually, there are deep thoughts behind this. Is this correct? Can you go infinitely small and take these numbers to be infinitely small, both of them? Can you divide them together, and then will that be a fixed limit? Well, not necessarily. In the world of the fundamental particles of nature, this is not quite right. In fact, that's not the exact way to define velocity of a particle. Something else happens, having to do with infinity. You can try to make these things infinitely small, but then it will not quite produce the velocity of particles. It does so, however, for planets in a very, very good explanation. So then Newton made a next step. He said, you take the concept of velocity, and again, you plot now not the position, but the velocity of the particles, and again, you take at a velocity change in a small time moment, delta t, and you again divide the two, and then you get another concept called acceleration. And, well, you know what acceleration is. If you sit in your car and you press the gas pedal real hard, and you feel the car being accelerated. But Newton realized that the acceleration of a planet is determined by its location in the solar system, by a force that was going to be called the gravitational force. And that gravitational force fixes the acceleration of an object once you know its position. And this way, Newton discovered the law of gravity. So for most of us, this is so logical and simple that we don't realize even that there are some deep thoughts here which could have been different. And in fact, for elementary particles, it is different. This is not the way to, not in general, to define how particles are being accelerated, because there are complications taking place. So whatever we say, never mind for planets, it works. But for elementary particles, as I said, this is not quite the same thing. An electron is an elementary particle, and it is the lightest and the smallest particle that you can study in daily life. And you find that that electron obeys certain properties. In spite of the fact that you cannot say it has any size, as far as we know, it's a point. It does have a property called mass, and also a property called electric charge. And besides that, it also has spin. So in spite of being infinitely small, it still can rotate around its axis. But rotation is not quite the right word for that. But it has an effect in it that we call spin, and makes the electron behave like a soccer ball that is spinning around its axis, or like a billiard ball or anything else that rotates. A planet also rotates in general. And the concept of spin can be attributed to an electron as well. And then in the first half of the previous century, it was discovered that if you knew the mass and the charge of the electron, and you knew the spin, and you know all these things now quite accurately, then you can calculate another property, which is the magnetic field. You see, moving charges generally generate magnetic fields as well. That's how a dynamo in your car and in your bicycle work. And quite generally, it's a property of particles that as soon as they spin, they go along with a magnetic field as well. And for the electron, you can calculate that magnetic field just because you know it has mass, it has charge, and it has spin. In certain units, when you measure this quantity, it is roughly the number 2. The number 2 suggests that some very basic feature of the electron that makes the spin, the magnetic field to be almost 2 units. When I say magnetic field, what I really mean is the strength as if the electron were a magnet. So electrons behave in many respects as magnets. The strength of the magnet, it can, in certain units, be identified as being 2. But it's not quite 2. But in the first half of the 20th century, scientists found out how to calculate the corrections on this number 2. And that is a very interesting calculation. When you do that calculation, you find that the electron would have been 2 if its interaction with a photon, the particle that carries light and electromagnetic field, if that interaction were just given by its electric charge alone. And if it were just given by this diagram, then the magnetic field strength of the electron magnet would be exactly 2 units. But now we have learned to think about those interactions in terms of diagrams. My talk will not be about how we got these diagrams. It was part of the Nobel Prize, of course, but not the most significant part because it was already known. Scientists long before us had already figured out how to write these diagrams to illustrate what calculations you still have to do to find the next decimal places beside the 2. If a photon is emitted here, and watch this pad here. If the photon is emitted and absorbed again here, and then just in the meantime the electron emits a photon, then it's oriented in a different direction, and so this diagram gives a correction to the magnetic field of the electron. But there are other diagrams as well, like this, and you have more complicated diagrams, and the sequence goes on and on and on. So I say, wait a minute, it goes on and on and on. Where do I stop calculating? Because I can't calculate on and on and on. And furthermore, these calculations become extremely complicated. These double diagrams here with 2 photons being here exchanged, that's an 8-dimensional integral. It's quite a nasty thing to compute mathematically. So fortunately, we are in a very fortunate position here. Whenever the diagram contains more of these closed loops, here's one closed loop, here basically you see this is a closed loop in a closed loop, these are 2 loops, and here also. The more loops the diagram gets, the smaller the contribution is. And this we know from general principles, so we don't have to go very far to get a very good outcome. So what we can do now is compare the calculated strength of the electron with the actual measurements and compare the 2. And what you get is something very interesting. The diagrams, term by term, described by these Feynman diagrams, give you certain numbers. You add all these numbers up to get the magnetic moment of the electron, and you find the number which, well, this was the measured number, this is the theoretical number. You find those numbers to be almost the same. They are not quite the same because we scientists cannot do infinitely accurate calculations. We must make approximations. We say, well, this looks about like that, so we just smuggle a little bit, and then we make small mistakes, inevitable. So the numbers don't exactly match, but we are all confident that if we manage to do the calculation more accurate and do the measurement more accurately, then the numbers will continue to match. It's not totally obvious, by the way, because the other electron, the other particle with which we can do this is the muon, and for the muon, the measurements and the calculations don't match that well. There's a little reason for concern. Maybe something is missing in our theory. But anyway, the most important feature is that up till this many decimal places, we understand what we are doing to calculate the magnetic field of an electron. And this was a marvelous accomplishment, one of the many accomplishments that scientists made in the previous century. It was around 1969 that I entered graduate school in my university at Utrecht in the Netherlands. And it was this gentleman who was just appointed as professor there and who had been working on not precisely this problem, but a very much related problem, because it had been figured out by very careful experiments that electromagnetism is not the only force to which the electron is sensitive. There are other forces called weak forces. Nowadays, they are called electroweak because these 2 different forces are related. But at that time, we didn't know that. Veltman knew that there were weak forces, and he also knew how to make theories for these forces. And from those theories, he had deduced the new Feynman diagrams that other force particles would generate in order to compute not only the magnetic moment of the electron, but also other properties, like how the electron can turn into a neutrino while hitting another particle, or the electron could elastically collide against other particles, and then the other particles would undergo changes as well. So this is just in words what was going to be the standard model of elementary particles. In those days, we didn't know anything about the standard model. We even didn't know how to write down the theory properly. But Veldman had his own theory about this that generated these diagrams. And but then he found out that when you compute such diagrams, that even, well, we didn't know, most of these diagrams were too small, or their contribution would be too small to contribute to the magnetic field of the electron, but you could apply them to other forces. And it seemed that his theory would reproduce the reality pretty well, but not quite. But he had a more basic problem than that. He had a confrontation with infinity. And that was that if you compute all these diagrams, this time something terrible would happen. And damn it, I'm so. And the terrible thing that happened would be that every diagram here generates an infinity. So what I have been doing here, I forgot to tell you just before, that all these diagrams are actually infinite in their contributions. But when you combine all infinities together, then by a sort of miracle, they all cancel out, and they give you a beautiful theory which gives this agreement. So the agreement did not come lightly. It only came when we knew how to handle the infinities that occur on these diagrams. And now in Veldman's theory, in all his new diagrams, he also generated lots of infinities. But this time, the cancellation did not work quite well. So what he found was that all these diagrams make the electron behave slightly differently. Well, not slightly differently, infinitely differently. So these forces generate something infinitely strong. And in spite of all these diagrams that he had, they did not cancel against each other properly. Actually, there was a lot more to say before even making that statement. Even before we did these calculations, the previous sequence of diagrams would not cancel that simply. They would only cancel if you did something else. You would realize the electron have a mass and a charge and a spin, but these properties also would be modified by those extra interactions. And even the modification in the mass of the electron due to this little loop here and this little loop here, these loops have an infinite effect on the mass of the electron. And these here have an infinite effect on the charge of the electron. So, but fortunately in this case, when you took these infinite effects into account first, and then you found the infinities of all the other diagrams, then if you were sufficiently careful, you found that all the infinities just beautifully cancel. And that is what gave this number. But now for the weak force, we have asked the same question. This time it didn't work. There was something terribly wrong in the rules that we wrote down. So Veldman was a strong person. You can see it already on the picture. He was quite powerful. So he didn't stop there. He said, okay, if it doesn't work, I add some extra particles to my system called ghost particles. These particles are not seen in the physical world. You will not be able to measure them or anything. So I can give them properties any way I like. And they only go around in loops. And these loops also generate infinities. So now I'm going to choose these ghosts such a way that those infinities cancel perfectly. Well, yes, but if you did that, then those loop particles would also fill loops. So now you have to ask, does this work when you take loops upon loops? He said, of course it does work, but no. He still encountered infinities. So we are running into a problem that was getting more and more awful. The infinities didn't stop here. In principle, you could say that what we did with electromagnetism alone was just like what Newton did. You know, you very carefully divide infinite numbers among each other, and you make sure that all the remaining infinities cancel out. And what was very easy for Newton to do in his time was now hard for us to do. But it didn't work, so we have to think again. In the meantime, there were 3 people, actually more than 3, because these are the 3 who later would get the Nobel Prize for their contribution. But there were other people who just only a few months later came with the same idea, but it was too late for the Nobel Committee. They only give prize to not more than 3 people, and then they take those who came with the idea first. These 2 gentlemen, Engler and Braut, had a beautiful extra ingredient in their theory. They took what we thought was the electroweak force, but then they added a particle, but this time that wasn't the ghost particle. No, it was a really physical relevant particle, except Engler and Braut didn't further mention that what they did was actually add a particle to the system. They added a field to the system. Just like I have electric fields and magnetic fields, there was a new field going to be added. And that field would, well, they didn't know whether actually this would solve the infinities, but they thought that this was a more elegant way to describe the weak interactions. It was Mr. Higgs who was held back. He sent in his manuscript around the same time that Engler and Braut handed in their manuscript, but Higgs' paper came back with a peer review. And the reviewer was a physicist, probably. We don't know who the reviewer was, by the way. They never tell. But anyway, it could have been Veldman, I believe, but because he would have asked the kind of question that was asked by this reviewer. The reviewer asked, what kind of changes does your theory bring about in the experimental situation? Are you predicting anything new? So Higgs was held aback by this rotten remark. Nothing new, what do you mean? There's something new. I have different field equations. But yes, what the effect of these field equations are is an extra particle. And he realized there's going to be an extra particle predicted. That particle will not have spin. In fact, it will not fit in a beautiful scheme at first sight. It will be a particle whose brothers and sisters in the theory are missing. It's just a single particle that sits there with such and such properties. You could write down all the properties. And that's the prediction of a theory. So the reviewer was quite happy with that statement. Your theory predicts something. Now, but that caused him a delay of a few months. But he was the one who came with the particle. So everybody started to call this particle the Higgs particle, and so did the Nobel Committee. So he was in, and together they received this prize. But we, Velp and I, knew very little about that. There were, well, this is something. We didn't really know about their manuscript. It was not very well known because this was field theory. And in our days, field theories were often looked down upon. Veldman was one of the few physicists who still believed in fundamental ideas expressed in quantizing fields rather than particles. And when you consider those particles to be the energy quantum of a field, then you solve many problems that you would otherwise not understand, including this nasty infinity problem. But field theories were not very popular in those days. So not many people were quoting this paper and were working with it. And Veldman was one of the few people who had seen these papers, but said, no, that's just mathematical garbage. Why should I add a particle that hasn't been discovered yet? And how can it be that that solves my problem? And well, it was when we started to work together that we saw that what these 3 gentlemen added to the theory looked like a very small change by adding a particle which is very difficult to detect, but it makes all the difference. Now all of the infinities will disappear. But that wasn't the end of the story. By the way, how much time do I have, Fabio?
Please.
How much?
30 minutes. As you prefer.
Okay, I'll just go on for some, and I can go on forever. So I can go on for, that's infinity again.
I will let you know.
Okay. Not all problems were solved, however. So once we realized that this theory was going to be a theory which needed no further ghosts of that type. The theory did need ghosts, but those ghosts had a firm mathematical background which we could understand. But it did not need ghosts of which you should guess the rules and then of the kind that Veldman originally looked at. So now we took again that theory, and now well, we had also discussions about this, but eventually Veldman had also constructed a computer program. Today, when somebody says he made a computer program, you can stand and join the row from behind. There's a very, very big queue of computer programmers before. But Veldman did something which hadn't been done yet at that time, which is give the computer a bunch of Feynman diagrams and let the computer directly compute those Feynman diagrams. More even, let the computer itself determine what Feynman diagrams there are. And then you just press the button, and if you wait long enough, you get the answer. But remember that computers in 1969 were less powerful than these mobile phones. It was, you might think it's not so easy to program a mobile phone to solve your Feynman diagrams. But even when you did that, not all problems were solved. Because, as I said, you divide infinity by infinity, or you subtract infinity from infinity. Does that give a finite number or not? If you're very careful, yes. But what does very careful mean? It means you have to compare different Feynman diagrams very carefully. And if you have regularized one of these diagrams, then the prescription for the other diagrams follows. But that's not easy to ensure that no mistakes will be made, or worse even, that maybe there is no way of making all these Feynman diagrams cancel exactly the way they should. We would call that an anomaly. And sure enough, anomalies had been discovered before that. In fact, my undergraduate work was based on the literature search of anomalies, called the Bell-Jarkiv anomalies. If there would be anomalies in these theories, that would ruin our whole program. So we needed to prove that there were no anomalies. How do you go about proving that? We tried all sorts of methods which didn't work. So we couldn't prove that the anomalies didn't ruin our whole theory. But we did know something else. You can put this theory in a different number of space-time dimensions. You know, today we live in a three-dimensional space, and there's a one-dimensional time. Altogether, our space and time have 4 dimensions. So if you work out this theory in 4 dimensions, it gets this very special property of infinity calculation. But you could write down a theory in 5 dimensions, or in 3 dimensions, or 2, and you get expressions for the Feynman diagrams that look almost identical. Not quite, because a number which is number 4 in the Feynman diagram will become a number 2, or number 3, or number 5, whatever you choose. And then the calculation can become a lot harder or easier. But the definition of the diagram is very well formulated. So, for instance, you can do that, but then it was found that when you write down the expressions in these theories, you get the Euler gamma functions. I didn't write them here. But these Euler gamma functions, which are defined here on this bottom line, you don't have to follow the equation if you don't know it. But if you have something with mathematics, this is a lovely expression. In mathematics, this is a beautiful mathematical function. A little bit like sine and cosine, a little bit different. And these functions enter, because the gamma functions, when these n's are integer, they are just the n factorial. So the factorial of n is the product of all integer numbers ending with the integer number n. Then you have n factorial. Well, this gamma function is related to that, and that's a function that enters to your Feynman diagram. Now, you can take the Feynman diagram, but not put it in 4 or 5 dimensions or something, but put it in 3.99 dimensions. And when I asked about Veldman about this, I was very afraid that he would just smash this whole theory in the trash box, because that means nothing, except that people who study these fractals, which I showed in the beginning, sometimes gave these fractals dimension. But what does 3.99 dimension mean? Well, literally it means that whenever you encounter a gamma function in your Feynman diagram, you just make this placement. Instead of n integer, here the number d can be given any value. We can take x to the integer power, x squared, x cubed, and so on, but square root of x and square to the power 1 over 10 is mathematically easily defined. So it is easy mathematically to put a whole theory in 4.5 or in 3.99 dimensions, do all calculations and see what happens. Now this gamma function has a very important property, that it every now and then becomes infinite. And that is the kind of infinities that we are worried about. But the strange thing is that the gamma is only infinite when n is itself integer. If n is fractional, and even though this definition this integral might diverge and generate infinity, you can trivially replace it by something finite. And then the calculation can be done again. And this was not a proposal. What was more important, however, we could easily see that if we integrate the diagram this way, then there could be no anomalies, because you could look at all diagrams one by one and see immediately in what way all the infinities cancel out. So we've understood the theory generates no anomalies, but that wasn't quite true. There was one circumstance where the theory did generate anomalies. So again, reason to worry. And in fact, the anomaly happens if, and now I'm making a little technical remark, the standard model of elementary particles contains quarks and leptons, and they both come in families. So we have 3 different families of quarks. We have 3 different families of leptons. The leptons are the particles to which the electron and the neutrino and so on belong, and the quarks are the things, building blocks of the protons and neutrons. But it turned out that if you have an equal number of quark families as you have a number of lepton families, then these anomalies again cancel out beautifully, and the theory works. And now let's look at the standard model. In fact, after this cancellation was realized, people searched very hard for the missing families of particles and found them all in due time. So today's standard model has exactly equal number of quarks and leptons, and so we know that the theory will work. We don't need any further changes in the theory for the theory to work just perfectly. So this was a great success. And although my time is running out now, I just want to give one little end remark. Because although our theory worked, and it was used in practice, even the dimensional regularization procedure was found very convenient for mathematicians, and all those other people who like to calculate things, they found the dimension renormalization is even simpler than if you try to use any other way to make the infinities cancel. But I had one colleague, Raymond Stora, this person, whom I had lively discussions with, because his problem was he didn't like Feynman diagrams. He literally felt uneasy with them. He didn't know how we were managing these diagrams. He said, I want a theory that works without diagrams. And he came with one proposition after the other, and I said, that doesn't work, that doesn't work. And then he came with something, and I said, that might work. And I asked him some questions, and I realized that not only it might work, it did work. And it was a fantastic improvement of what we had done. So we are not no saints, there are things we don't see, and they had, the 4 of them together, actually these 3 worked together, but Mr. Tooten had the same result all by himself at around the same time. Becky, Ruestora, and Tooten discovered that the new ways of phrasing the Feynman rules that we needed obey new symmetry equations. So they discovered a symmetry that we simply hadn't seen. Well, to be frank, I had seen that the way I would manipulate those diagrams would be very much the way I would manipulate symmetries in these diagrams. But my conclusion was this isn't a symmetry because all the signs are wrong. And so what these gentlemen did, all themselves, is said, yes, if you choose the other sign, you get another concept of symmetry. It works just as well. This is our symmetry, the BRST symmetry. And with BRST, now textbooks could become a lot thinner, because now all the textbook writers say, and now we're going to apply the BRST theory. We need only a few lines to describe what it is. It's far from trivial. It's a very ingenious discovery, but they made a discovery, and then we say, and now we continue from there, and now you can see everything works. And if you want diagrams, fine, but if you want to do your calculation any other way, it is fine as well. So that is our fate, and I think that happens very often in science. The first time the Higgs particle was discovered experimentally, it was a lot of work, and you saw a very tiny little beep. And now it's a big beep standing out, because scientists found better ways to measure these things and to improve the laboratory also. So things go better and better. But that happens everywhere. Maybe Newton really had a problem with defining velocity, and only after a large amount of time, he came with this definition. And nowadays we say, well, you just look at the speedometer of your car and you know what velocity means. So if you have anything other to tell, I don't need it anymore. That's true today, but it wasn't true in all days. And so this happens in many, many branches of science, that first discovery is made, and it's a hell of a lot of work to understand what the discovery is telling us, but then later people say, well, it just means this and this and that, and now we can squeeze it in a thing that goes into a pocketbook very easily. So this was our fate also, and this is, but you see that we confronted infinity. Infinity is confronted in many other modern theories as well, where we have no solutions to the same kind of questions. So questions involving symmetry are still haunting us, but I think we can draw lessons from the past. I think I should thank you here. Happy century-versary to the University of Padua. Thank you.
Thank you for this wonderful story of research. So I'm a philosopher of science, so I love your struggle, this wonderful struggle with anomalies, for symmetries and so on. So I have a couple of questions, but the priority is for the audience. So we have a few minutes for questions, and so please, it's up to you. You have questions for Professor Hooft? It's a great occasion, mostly for students there. Don't be shy.
There exist no stupid questions.
Yes, but it's
there exist stupid answers, but not stupid questions.
I have to remind that a question is a short sentence with, at the end, a question mark. So please. We have also great physicists from the University of Padua here, so if you want to be part of the discussion, please. So I start with my question. So I try to be because let me understand if I understood well. So in this story of research, to find infinity implies that you are wrong in something. So infinity means that it's meaningless. Also the description. So why? Because with respect to in Newton time, so Newton wrote that we have outside an infinite space and absolute space. So you are physicists in a finite world, and so when you find something that is not finite, it's a problem. Well, so why?
You're absolutely correct that sometimes infinities are less harmful for our understanding. So saying that we are in the infinite universe doesn't change anything we know about elementary particles, at least not directly. It would change our view of cosmology, where the question whether the universe is actually infinite or not makes some differences. But in that case, you can still argue maybe the universe is infinite, and we have to deal with that. I would not be totally happy with such a theory, but it's true that some infinities are quite harmless. Of course, you can ask the question, if you make a sequence of prime numbers, where is the last prime number? Then mathematicians will say that's infinite, because that sequence doesn't stop. It's an infinite sequence. So mathematically, you can define infinite sequences rather easily. But if you say prime numbers play a role in physics, and in some cases they do, then you can ask, where does a series stop? But then, in the formal sense, infinity doesn't stop. But in many cases, it is harmful. So if you calculate what is the effect of this particle, that particle, what does it do to the mass of this particle? And if you say, that effect is infinite, then you say, I don't understand what it means for a particle to have an infinite mass. The same thing for charge or other forces. If the concept you're talking about doesn't mean anything when you substitute the number infinity, then we have a problem.
Yeah. So, question please. Piero? Maybe you can use the same? No, not the same.
Thank you. In the audience, there are quite a large number of young person, probably a number of them will be our students. If you had to recommend them which kind of path to follow for their thesis, probably a number of them is going to come to our offices and ask for thesis, for recommendation for either PhD or master thesis. Given your experience, given the status of the field now, is there anything that you feel as recommending to them for the prosecution of the studies?
I think, to me, the question falls in two parts. One is a very general answer. You should follow it, but it holds not only for physicists, but for everybody. You should follow the path where you feel that you can do something, where you feel like you have some ideas. And so both my daughters went into very different kinds of activities. My youngest daughter is a veterinarian because she loves to go to work with animals. And because she was so happy with animals, of course my advice was do a veterinarian study. And in general, I would advise that kind of thing to anybody who wants to go into physics. Physics is a very wide field of activities. There are many, many branches of physics. All of them have come with their own challenges. So if you feel like you can make a difference in this particular challenge, then that's where you should specialize. But as long as you don't know, and you say, I like all of physics, then study all of physics until you hit some really challenging question in there, and you say, okay, I started 3 years or 2 years or whatever doing all of physics, but now I hit upon something that I find so interesting, I want to focus on that. So for some people that will be cosmology or particle physics. There are a number of unanswered questions, and that's basically my second reply, is if you really have decided that physics is going to be your field, then you have to know that there are some big questions and there are small questions. The big questions are the undecided questions which are making a big difference in our world if we knew the answer, such as how does the gravitational force fit in with the other force laws of our particles. There are very fundamental problems there, and we haven't been able to answer those questions, not to my satisfaction. Some people say the string theory is the answer, and you can't add much news to that. I'm not totally happy with the string answer to the question, what is gravity? There should be more to be said about it. There are fundamental questions even in quantum mechanics, but the danger is there, the traps and pitfalls that you can fall into. Because lots of the problems that people are encountering in quantum mechanics, to my conviction, are sort of pseudo problems. They're not real. They're imagined because people still don't quite understand what quantum mechanics is, to a level needed to understand that the problems that they see are not real physical problems. So there's a little warning sign there. If you want to go into that field, watch out, watch your step, be original and believe in yourself, and be extremely critical, primarily for yourself. So if you think you have a result, think twice. Is this really a result? What will the criticists say about my result? And they can imagine very quickly, oh, they'll say this and this and that. And so imagine what your answer will be before becoming public with that result. And so that is also a general remark. But addressing the challenging big questions is, of course, a very nice thing, but there are only very few of such questions, and there are probably many of you who want to go into physics. But physics has many other very interesting challenges. For instance, how to make the best telescopes, how to make the best particle accelerator, how to do calculations better than anybody could do them before. There are many such questions, and they all require a very great amount of specialism and special research in particular fields in order to be able to feel at home in that field. But you must make sure that you are doing something that not so many other people are also doing. If you join a big crowd of people, then you only get a little amount of reward. But if you manage to define a subject all by yourself, then chances that you'll make success, well, they are reduced for other facts, namely the big odds are that you are wrong. But if you believe really in not being wrong, then this is a very interesting field for you to go into.
Daniel, please, here.
Thanks.
Thank you very much. I was thinking that, speaking of infinity, you can have infinitely large or infinitely small numbers or parameters. Some years ago, you observed that a parameter, for instance, the mass of the electron that you mentioned, could be naturally accepted to be a small number because sending it to zero, you were increasing the symmetry of a theory. However, you know that for other fundamental parameters in the universe, for instance, the mass of the Higgs boson that you referred to, the value of its mass is not directly related to a symmetry of a theory. I was wondering if you think that having fundamental parameters deciding about the evolution of the universe infinitely small is something that we have to accept as just a matter of fact that these parameters are small, or if they are unnaturally, to use your word, small, we should find some explanation about this infinitely smallness of these parameters.
Well, again, a discussion is also divided into. One is more general. You're talking about numbers in physics which have a certain domain of values, very small, very large, or anything in between. And we physicists have been puzzled by many of such numbers. For instance, the mass of the proton is more than 1,800 times as big as the mass of the electron. Where does that number, 1,800, come from? Similar thing with the electron and the muon. The mass difference is rather large. Where do these numbers come from? We have no answers today. So today's theory is measure those numbers, then we can tell you what the particles do. But there's more than 20 numbers that have to be measured because we have no way what to do. We don't have any way even to relate those numbers to each other. They are just falling out of the sky. And we can measure them as accurately as we manage to do. And then we can say the rest about the theory. That is not a comfortable situation to be in as physicists. As a physicist, I would say, no, I don't accept any theory where numbers are just falling out of the sky. I don't want anything to fall out of the sky in this theory. I want to have a complete explanation as to why the numbers are the way they are. That includes large and small numbers or whatever you have. But now you mentioned, and that's the second part of the question, you mentioned a more special situation, namely it looks very unnatural for some numbers to be what they are. For instance, and the Higgs mass is one of the better examples of this. There was an example in the 20th century, long ago, that said that the pion is much heavier than the eta meson, whereas the eta meson obeyed exactly the same rules as the pion and had exactly the same symmetries. So why is a pion so much lighter than the eta? And well, I said exactly the same symmetries. No, there was one subtle differences in the symmetries, but we couldn't understand why that would make the pion so heavy compared to so light compared to the eta particle, until it was realized that there was a reason, which was a special solution of the equations, which was acting on the eta particle fundamentally differently than on the pion. And so we then suddenly started to understand why the eta is so much heavier. So yes, that is a satisfactory situation that amount you understand, but still we have difficulties in defining how to measure the eta particle mass, how to calculate the eta particle mass. It's still a hard problem. But understanding comes in small steps. So eventually my answer is to your question, we want to understand all numbers, big and small. The Higgs, by the way, well, to me, the Higgs, having the mass it has, that mass is 10 to the 17 times smaller than a fundamental mass in nature called the Planck mass. So my answer to that is maybe there's an underlying theory that says that once in 10 to the 34 times that two particles hit, they do this, and in all the other cases they do that. And that means that there's a symmetry which is broken only once in 10 to the 34 cases. And that is an indication that somewhere in nature this remark must be of importance. But I'm just giving a very stupid answer now to the question because I don't know how to continue this statement. I don't know how to make that theory work. So I can call the number 10 to the 37 as an undesirable number to come falling out of the sky. But and I just gave you the beginning of what could be a theory of the future, but that theory doesn't yet exist. So there's work to be done in particle physics. These are, by the way, some of the deep questions that I just mentioned. That if you're interested in those questions, and if you have an idea that you have an approach that will make the difference, then you could at least study those theories as accurately as you can.
Before we have a student, and then this.
Yes, I wanted to ask two questions. The first is, how is the problem of infinities in quantum field theory related to the interactions being point-like? And secondly, if I want to ask that the success of the renormalization program, does that mean that interactions are actually point-like, or is it just a bookkeeping device?
Okay, your question about interactions being point-like, it is true that, particularly in the 20th century, in the first half of the 20th century, people put their finger on those point-like particles and say that cannot be true. They must have a size somehow. However, as soon as you give the particle a size, it will no longer be invariant under special coordinate transformations. So Einstein's theory won't work so well for particles which are not point-like, because particles will stretch and they'll become line-like in no time. So, that is, if particles are fundamentally point-like, that doesn't happen. And in quantum field theory, the fact that particles are point-like has the effect that interactions happen at a single point. So you have two fields, and the product of the two fields is equal to a third field at a point. That's the point where the particles of these two fields interact to make the third particle. But that can only make sense if the particles are all point-like. So being point-like is very important. If you deviate from that, you run into much more problems than you're actually solving. So in our standard model, all the elementary particles in there are points. However, we realize they won't be points forever. That sounds silly. And what you said was right. Why not say that they are some fluffy stuff of some sort? And yes, that is probably true. But then you have to come with a very powerful argument as to what substitutes that point. And that is so difficult in practice that you say, no, we do one thing at a time. We treat all these particles as points until we are really forced to make them lines or something more complicated than that. And as long as we are not forced into it, we don't, because we are making our life a lot more difficult than we think necessary. The point theory works for particles and works for quantum fields.
First line, thank you.
Well, somehow my question is related to this one, in the sense that you started your seminar talking about gravity, you ended up again talking about gravity, because we know that in the gravitational theory, if we try to quantize it, as a quantum field theory, we have this problem of infinities, and we don't yet know exactly how to tame these infinities if we just treat gravity as a quantum field theory. Now, you said yourself, that there is an option, which is string theory, which somehow thinks about these fundamental entities in a different way, and in a clever way replaces the particle and introduces new symmetry principles in some sense. And so, since you saw that symmetries have been important in order to tame these infinities also in quantum field theories, why you think that you have all these reservations about string theory.
Say it again, the last sentence.
Why you said yourself before, no, that string theory you don't think is still the right way to quantize gravity somehow, no, to describe really gravity and resolve these problems. Can you elaborate on that?
Well, we found very frequently, there are many instances in the history of science that when people start to ask smarter, sharper questions, that they get sharper answers by nature, by experiments, and so on. So Einstein asked, how can it be that a particle with a certain velocity still obeys electromagnetic equations? And the answer was because the particle changes its shape when it has a very high velocity. And there's a famous Michelson-Morley experiment had been done already that seemed to indicate this. And so, so asking very sharp questions makes progress. But my experience is that making assumptions right in the beginning of your theory is a weakness of your theory. The assumption will begin as being a marvelous thing to start off from, and you discover many new things. But after a while, you hit upon problems, and the problems are, is this original assumption correct or not? And that's my problem with string theory. The assumption is particles are strings. When they say that, they discover they can't add point particles to that theory. So all particles have to be strings. And then they say, yes, but there are infinities. Maybe some particles are not strings, but membranes. And then they say, maybe not membranes, but more fluffy things. And that sounds like going into a path where the difficulties are going to pile up. And the reason might be this first assumption wasn't really the assumption you should have made. They should have asked all of nature to be controlled by laws that are more efficient than the laws we have today. What are more efficient laws? And one of those questions I'm asking now is black holes. Black holes are a consequence of Einstein's equations, but the laws they obey are not right. If you apply Einstein's equations without changes, you get a self-contradictory situation. So the question is what to do about this. And I like such questions better than the assumption, let's say particles are strings, and let's see where we can come from there. The strange thing is I get equations that look very much like the equations of strings, but applied in a very different way, without the assumptions that particles are line-like. So that is my preference. Of course, there's no guarantee, no matter what you do, there's no guarantee that you make progress in science. You might just make a step backwards. But sometimes making a step backwards is not so bad. You know, the French saying is reculer pour mieux sauter. That's sometimes a very good advice. Better assumption than assuming something that you don't really know about.
Another one here, before students. And then we have another colleague here, and then Fabio.
Good evening, Professor. I'm a master degree student. My question is about dimensional regularization. So you talked about how it handles very efficiently infinities in quantum gauge theories. Now, studying it, I was quite puzzled because my question, I guess, was how seriously are we to take quantum gauge theories in fractional dimensions? For example, you mentioned fractals, which are strictly related to fractional dimensions. And so, and we know that, for example, the dimensional regularization approach has some implication, like the need to introduce a renormalization scale in the theory, which has deep consequences on the physics of the theory. So are we really to take very seriously quantum gauge theories in fractional dimensions or not, I guess? And what may be the role, a more physical role of a fractional dimension, I guess? Thank you very much.
Yes, of course, what you are asking now is a question, you know, what does it really mean what you say? And that's a very important question. And I asked this question myself many times. What does it mean to say that space and time have a fractional dimension? Does it mean that space is a fractal? It could be something like that, and but we don't know how to continue from that point on, how to make the theory work. So we took the poor man's position because we can't do any better. If we could, we would certainly have done better than that. But the poor man's position is just look at these Feynman diagrams. We know exactly how to define them. We know how they all stand for some integral expression that you have to calculate. Let's take all these diagrams, and that's everywhere where you take them for all number of dimensions. Wherever you get a dimension n, replace that n by 3.999, and then not an integer. And then the calculation is going to go just as smoothly. Mathematicians say have no difficulties at all to do that calculation. The computer goes about as fast as when the number were exactly 4 or 3. And then we can continue from there. But the procedure does not tell me what it actually means, what these Feynman diagrams are now standing for. And I think that is an important question, and it may be a weakness of the theory. So I was surprised that it worked so well that people embrace the theory and they say, now we have easier ways to compute integrals, because it works better if you leave the number of dimensions adjustable for a later stage. So it works so well that many people are not asking the question, but your question is very well taken, and I'm still asking it myself, and I don't get answers.
Good point. Congratulations. First line here.
Hi, Gerard. Well, as you know, when you work with point-like particles, quantum field theory generates infinities, which can be good ones or bad ones. In other words, in the theories you described, the infinities can be lumped into a finite number of non-computable quantities, like masses, charges, and so on. But when you go on to gravity, or say you want to quantize Fermi's theory, these infinities proliferate infinitely many times, and you lose predictivity. So my question is, these days you tend to regard local quantum field theories as effective theories, which are good up to a certain energy scale, and the fact that you don't know how to go to infinitely short distances, you have to pay a certain price, okay? So people give a lot of importance to studying theories, to constructing theories which are ultraviolet complete, okay, which can be trusted up to infinitely short distances. For instance, quantum chromodynamics is one such theory, but not the electroweak theory, not even quantum electrodynamics is such a theory. You cannot remove the cutoff. So what I'm saying is that I'm trying to speak in favor of extended objects, because if you have extended objects like strings, all these ultraviolet infinities completely disappear. So you have to admit that having extended object solves one big problem with local quantum field theory, the fact that you have to put your infinities under the rug somehow. You have to admit ignorance about the true physics down to every possible short distance.
Okay, I'm quite happy to admit that ignorance. I don't quite understand physics beyond the Planck scale as what you're talking about. That's exactly... So, well, not perfectly, because as you say, it generates infinities, which this time cannot be renormalized. Not in string theory, I know it's finite, but I have this problem with string theory that it uses an assumption, which actually it's the same objection you can add to many theories, that you don't like the assumptions. And the assumption in string theory is an assumption, it's a string. But why should we stop there? The next step is that we should add membranes. And from membranes, you should go to higher objects. And the question is that so bad? Well, maybe you say no, That is a natural way of things to go. String theory goes to 26 dimensions, so it would be the 24 brains that could still be something non-trivial. Yeah, it will be complicated. But there's then a deeper, maybe I should mention my other objections against string theory, it is fundamentally based on perturbative expansions. And you can't sum the perturbation expansion directly. It's even worse than in many field theories. Even if the first or second perturbative correction becomes too hard for string theory to compute. I never really tried it, but they tell me that.
Local quantum field theory down to 0 size.
Yes, but no. The truth is, I don't believe in quantum field theories in that domain at all. I don't think quantum field theory will remain quantum field theories because, because what? The way string theory describes gravity is very different from gravity itself. You are basically departing from Einstein's relativity principle. It's no longer that simple. So when you say extended particles are ideal for solving this problem, I don't think so, because you have to say what are they made of, these particles, these extension of what? You know, what is it, linen? Is it rope? Is it iron? What kind of material is connecting these endpoints of these particles? What are the endpoints looking like? So you're not completely out of the woods by making such an assumption. You have to answer the next question. What are these? What is this material that strings are made of? But okay, that's one question. I have a related question, which is, of course, how to do perturbation expansion, and what is it expanding at all? Because strings are perturbatively defined notions, which you have to add up. You have the string analogs of Feynman diagrams, which are a lot more complicated to do. And basically what you're saying, well, I command that these diagrams add up to something finite and so on. I'm not totally happy with that way of phrasing a theory. Or I think that, well, yeah, I think we could add more points even where I have my doubts. The string theory is not the final answer. It is a very good attempt. And I would admit immediately, if nobody was doing string theory, I was doing string theory. But there's a huge group of people doing string theory, so I say, no, I'm going to make a different assumption, see where that brings me, and leave these extended particles for what they are for a moment. In fact, the horizon of a black hole is an extended particle, and maybe that's the thing to go to. And that's quite possible, that in the very end, I'll have to admit that what I'm doing is string theory. That could happen, but I want to see how that comes about, and not by making that assumption.
Now, Fabio? No? You are proposing a final solution for this wonderful confrontation between quantum gravity and string theory?
My question was already answered in the course of the answer to another question.
Okay, so it was a great moment of confrontation between these two great models in physics. Just a final curiosity related to the picture of Research Day in your field. What do you reply to the objection, to the criticism, according to which physics today is too much dependent on technical advancements with respect to theoretical physics? So new particle accelerators in order to have new physics. Because it looks like you are very confident in the power of theoretical physics. What's your idea?
Well, I gave sort of an answer in my lecture at the end when I said, no, we finished a theory, it looked beautiful, but it was very technical. And then came these 4 people who made an enormous simplifying observation. They say it's not that technical anymore, it's just a symmetry. Symmetries are not extremely technical, and we can handle them mathematically very well. But it's not as simple and ideal as we would like it to be. We will be able to teach it to our nursery school children and not to graduate students of 18, 19, 20 years old, then who have all the tactical abilities brought into them in an entire school life. So yes, today's answers to our fundamental questions are complicated and technical. But I think that the road towards the answers maybe as technical as it needs to be. But in the very, very end, our final answer should be as simple as possible. And now the standard model, already the word standard model suggests it's something fairly simple. And that's true, it's extremely simple compared to what people came up with before the standard model was there. You should see those ideas. They were all very complicated and technical. And nowadays, fortunately, we found out they were also wrong. So the standard model is a simplification. It is not as simple as what it will be perhaps 100 or 1,000 or 1,000,000 years from now, when computers did the rest to say, actually, the truth is much simpler than this. It's just wham, and then you come with one equation. That's what we really would like to have. But that goes step by step.
So thank you. It's been a great lesson of science and matter for our students. So thank you so much for being here at the University of Padua.